Japan sits on one of the most dangerous seismic boundaries on Earth, and right now, scientists are watching closely. Beneath the Pacific, immense tectonic forces continue to build in silence, storing the energy for an earthquake that could reshape coastlines, cities, and millions of lives in a matter of minutes. In this video, the story goes deep beneath the ocean floor to reveal why experts are seriously worried, what the science really says, and why the next great quake could come with almost no warning. If this kind of deep cinematic science documentary is compelling, please like the video, subscribe to the channel, and stay with the story. Far out in the western Pacific, Japan rests along the edge of a restless ocean realm. From a great height, the islands appear as a long, curved arc set between open water and the broad lands of East Asia. They do not sit in the calm centre of a continent. They stand instead at a meeting place, where the seafloor moves, bends, and sinks over spans of time so large that human memory can hold only a small part of them. The wider setting gives the first clue to why earthquakes in and around Japan draw such careful attention from scientists. Before any fault is traced, before any instrument is checked, the shape of the region already shows that this is one of the most active parts of Earth. The Pacific around Japan is not a still plain. It is a mosaic of plates, the immense slabs of rock that make up the outer shell of the planet. A tectonic plate is a broad section of Earth's rigid outer layer that moves slowly over deeper and hotter material below. These movements are too slow to see in ordinary life, yet they never stop. Over many years, they carry seafloor across ocean basins, press crust against crust, and drive one plate beneath another. Japan lies where several of these moving parts come together. This alone is enough to place the islands within a region of constant strain. The wider Pacific basin, when viewed as a whole, is not simply an expanse of water. It is a system of motion. Around the rim of the Pacific, long chains of volcanoes, deep ocean trenches, and frequent earthquakes form a broad belt that wraps around much of the ocean. Japan belongs to this belt. The pattern is not random. It reflects the slow descent of oceanic plates beneath other plates at the edges of the basin. Oceanic crust forms far away at spreading ridges, cools as it ages, grows denser, and eventually begins a return journey downward into the mantle. The mantle is the thick layer of hot rock beneath Earth's crust. It moves slowly over deep time, carrying heat upward and helping to drive plate motion. In the western Pacific, this returning movement becomes especially important because old oceanic plates approach the island arcs of Japan from the east and southeast. The broad geography of the region is therefore also a history of motion. The ocean itself gives little outward sign of this process. On calm days, the surface can look plain and uniform, marked only by changing weather, shifting light, and the long movement of swells. Ships cross these waters, fishing grounds spread across them, air routes pass above them. Yet below the surface, the seafloor is far from level. It rises in ridges, falls into trenches, and carries scars from ancient volcanic activity and constant deformation. Japan's place in the Pacific is defined not only by the islands that break the surface, but by the unseen contours beneath the sea that surround them. In this outer setting, the country is not isolated from the ocean. It is shaped by it. To the east lies the vast Pacific Plate, one of the largest tectonic plates on Earth. It moves gradually toward Japan. To the south and southeast, smaller but still powerful plate systems also converge toward the region. To the west, the broader continental margin of Asia provides a different kind of crust, thicker and more varied in structure. Japan occupies the narrow space between these domains. This is why the islands form an arc rather than a block, Their shape reflects pressure, bending, uplift, and repeated rearrangement. The mountains, basins, and coasts of Japan all belong to this larger setting. But in the outermost view, the most important fact is simple. Japan stands at the edge of an ocean basin whose floor is in motion and whose margins absorb that motion through earthquake and uplift. Experts who study earthquake danger begin with this setting because it governs everything that follows. A single earthquake may begin on a fault, but the long-term threat comes from the larger arrangement of the plates. In Japan's case, concern does not arise from one unusual moment alone. It grows from the knowledge that the region continuously stores and releases tectonic stress. Stress, in this context, means the force per unit area that builds in rock as plates push, pull, or slide. When rock can no longer hold that strain, it breaks or slips, and an earthquake occurs. This does not mean that every part of Japan is equally threatened at every moment, nor does it mean that scientists can name the exact time of a future rupture. It means that the broader Pacific setting supplies a constant source of energy, and that this energy enters the Japanese region through plate interaction over very long spans of time. The climate and human use of the Pacific add another layer to this outer region, though they do not create the earthquakes themselves. Japan is a maritime nation. Its people look outward across the sea for transport, food, trade, and weather. Ports, shipping lanes, fisheries, and coastal cities all face the same ocean basin that carries the tectonic forces toward the islands. This gives the Pacific around Japan a double meaning. It is both a route of connection and a source of danger. The same open water that links Japan to the wider world also lies above the zones where major undersea earthquakes can disturb the sea floor and send destructive tsunami waves toward shore. A tsunami is a series of long sea waves caused mainly by sudden displacement of water, often from undersea earthquakes. In the broad outer setting, sea and seismic risk belong to the same frame. The atmosphere above the Pacific can shift from clear light to storm and fog, but these changes are temporary. The tectonic setting beneath remains, season after season. The surface environment changes while the deeper arrangement holds its slow course. This contrast is one reason the science of earthquakes requires patience. Human attention often fixes on dramatic events, but the wider Pacific setting reminds observers that the region is always active, even in quiet years. Instruments may record only small changes from day to day, yet the plates continue to move, and the structure of the basin continues to load the margins of Japan with strain. In this outermost view, Japan appears neither as an isolated chain of scenic islands, nor as a place defined only by individual disasters. It appears as part of the Western Pacific system, set along one of Earth's great active boundaries. The ocean basin to the east is immense. The plate motions are slow, and the consequences of those motions can be severe. This is why concern among experts remains steady even between major events. The concern begins here, in the largest frame, where the Pacific meets the island arc and where the quiet surface of the sea covers a moving world of rock below. Along the outer edge of Japan, the meeting between land and sea forms one of the clearest records of life lived under seismic risk. The broad Pacific setting gives the first explanation, but the coast gives the first human answer. Here the islands present their margins to the ocean through harbours, fishing ports, industrial bays, river mouths, beaches, steep headlands, and low plains. These shorelines are not only natural boundaries, they are zones where memory, engineering, and daily routine gather around the possibility of shaking and flooding. The shape of the coast, the texture of the towns beside it, and the quiet arrangement of roads and barriers reveal how a nation adapts to repeated disturbance from the sea and the ground beneath it. Japan's coastline is long, deeply varied, and intensely occupied. In some places it bends around narrow inlets, where steep slopes descend into sheltered water. In other places it opens into broader bays edged by reclaimed land, warehouses, quays, and industrial complexes. Elsewhere, low coastal plains stretch outward from river systems and support dense cities, transport corridors, and fields. This visible diversity matters because earthquake and tsunami risk do not meet every shoreline in the same way. A narrow inlet can concentrate incoming water. A broad, flat plain can allow water to travel far inland. A steep coast may reduce one form of flooding while exposing roads and villages to landslides or intense local shaking. Even before entering the deeper geology, the coast shows that hazard is shaped by form. On ordinary days, these margins are busy and practical places. Fishing boats return to port, ferries move between islands, freight passes through container terminals. Families live in towns set between the sea and nearby hills. Seawalls run along parts of the shore, sometimes low and almost unnoticed, sometimes tall and severe, built from concrete in long grey lines. Their presence expresses a sober understanding. They do not suggest that danger has been eliminated. They show that danger is expected. Stairways to higher ground, marked evacuation routes, raised roads, floodgates at river mouths, and carefully placed sirens all belong to the same quiet logic. The landscape itself has become a manual of response written into concrete, slope, and street. These visible measures are strongest in places where past disasters remain vivid. In many coastal communities, the built environment bears the imprint of earlier tsunamis and earthquakes. Some towns preserve stone markers that indicate where floodwaters once reached. Others rebuilt on higher ground after severe loss. In modern districts, schools and public buildings may stand on elevated sites or be designed as vertical refuges. A refuge in this sense is a place intended to give immediate safety during an emergency, especially when horizontal escape is too slow. These responses are practical rather than dramatic. They reflect repeated observation that the coastline is both a resource and a line of exposure. The coast is also where the difference between long-term scientific knowledge and short-term human action becomes most visible. Scientists may describe probabilities over decades, estimate possible wave heights, or map zones of expected inundation. Inundation means the covering of land by water. Local authorities then translate these assessments into coloured hazard maps, signage, drills, and building guidance. The result appears in small details. A road sign points uphill. A public board marks sea level and evacuation sites. Breakwaters guard harbour mouths. Emergency supply depots sit above likely flood levels. These details belong to no single earthquake. They arise from the understanding that severe events recur, even if the exact timing remains uncertain. The coastal plain of eastern and southern Japan often carries a particularly heavy burden, because it supports dense settlement and critical infrastructure. Factories, power facilities, rail lines, highways, and port systems frequently occupy low land close to the sea. Such locations are economically useful. They allow easy access to shipping and flat ground for construction. Yet they also increase exposure when strong shaking or tsunami reaches the shore. Land that has been reclaimed from shallow water can be especially vulnerable to ground failure during earthquakes. Ground failure includes processes such as liquefaction, in which water-rich sediment temporarily loses strength and behaves more like a fluid. Though the deeper mechanics belong to later layers of the subject, The surface signs are already plain at the coast. Wide industrial zones and level artificial ground bring practical benefit, but they also add fragility. In quieter fishing settlements, exposure takes another form. A village tucked into a narrow bay may depend on the very shape of the inlet that also increases tsunami risk. Homes, boat sheds, small roads, and harbours often fit into the limited flat land at the water's edge, while forested slopes rise close behind. This arrangement creates beauty and shelter in ordinary weather, but it leaves little room for escape when the sea withdraws and surges back. The coast in such places teaches a hard lesson in geography. The same landform that supports a community can also channel danger toward it. Even where seawalls and evacuation systems are strong, experts remain careful in how they speak about protection. Coastal defences reduce risk, but they do not erase it. A wall is designed for a certain level of event, informed by engineering judgment, past records, and available resources. A future earthquake or tsunami may differ in size, source area, or local effect. Observations indicate that planning and infrastructure can save many lives. It remains uncertain in advance exactly how any single future event will interact with a given stretch of coast. This measured uncertainty is part of the scientific view. It does not weaken the value of preparation. It explains why preparation must remain flexible, and why no single defense is treated as complete. The coastline also records social memory in less visible ways. Regular drills in schools and workplaces, public education campaigns, local disaster museums, and community associations all help preserve practical knowledge from one generation to the next. Along the coast, this memory tends to remain more immediate than in inland areas, because the sea is always present. The tide moves in and out against walls and quays. Harbour towns rise each day with a direct view of the medium through which tsunami travels. This constant presence encourages a habit of watchfulness that becomes part of civic life. Seen from above, Japan's coasts may appear as thin lines between blue water and green or grey land. Seen more closely, they are complex human margins shaped by repeated negotiation with risk. They hold trade, food, industry, memory, engineering, and routine within a narrow band where the Pacific meets the islands. The coast does not explain the origin of earthquakes, but it shows how the outer setting is already translated into ordinary space, seawalls, raised ground, evacuation paths. And clustered settlements all stand as surface expressions of a deeper truth. Japan's concern about earthquakes begins far out in the Pacific, but it becomes visible here, along the shore, where the nation faces the ocean each day. Beyond the visible coast of Japan, the exposed sea surface forms a wide and shifting belt where warning begins. It appears open and almost featureless from a distance, yet it carries some of the most important early signs of danger. Between the deeper Pacific and the settled shore lies a monitored space of waves, pressure changes, seismic signals, and electronic transmissions. Here the nation extends its attention outward across the water, not to stop earthquakes, which cannot be stopped, but to recognize them quickly and turn a few seconds or a few minutes into action. This offshore warning belt belongs to the surface of the sea and the systems placed upon and beneath it, where observation becomes the first practical response to a threat arriving from below. The sea east and south of Japan is rarely empty in a scientific sense. It is crossed by ships, fishing fleets, patrol vessels, and research platforms. But more important for earthquake safety is the quieter presence of instruments. Some are fixed to the seabed in deep water. Some are attached to cables. Some float or mark positions at the surface. Some measure the movement of the ground. Others register changes in water pressure so slight that they would pass unnoticed in ordinary life. A pressure change at depth can reveal the passing form of a tsunami long before the wave becomes dangerous at the shore. In this outer monitored zone, the sea is treated not only as water, but as a medium that carries information. The first signal of a major offshore earthquake usually arrives not through sight, but through vibration. Seismic waves move through rock much faster than tsunami moves across the sea surface. Instruments nearest the source detect the shaking and send data to processing centers on land. A seismic wave is a pulse of energy that travels through Earth after sudden movement on a fault. Some waves arrive quickly and carry the first sign that rupture has begun. Others follow and often bring stronger motion. By comparing arrival times and signal strength from many instruments, scientists estimate where an earthquake begins, how large it may be, and whether it is likely to have displaced the sea floor. This early estimate is not perfect. In the first moments after a large rupture, the full size and extent of the event may remain uncertain. Even so, rapid detection is essential because delay shortens the time available for warning. Far above the hidden fault, the surface sea may look unchanged during these first moments. The horizon remains level. Wind continues to move the water into short crests and longer swells. Sunlight or cloud shadow passes over the same expanse, yet somewhere beneath, rock may already have shifted over a large area, lifting or lowering part of the seabed and disturbing the water column from bottom to surface if enough water is displaced. A tsunami begins as a series of long waves that may be small in height in deep water, but immense in length. Because the wavelength is so long, vessels far offshore may notice little or nothing as the wave passes beneath them. This makes instrument networks especially important. Human perception at sea is limited. Measurement extends that perception. Japan's offshore warning belt therefore depends on speed, redundancy, and wide coverage. Redundancy means that more than one system is used so that warning does not fail when a single component is damaged or incomplete. Seismic stations on land provide one layer. Seafloor systems add another. Buoys and pressure sensors contribute another. Satellite positioning also helps track slow changes in the shape of the crust and can improve the understanding of large events. No single instrument tells the whole story. The strength of the warning belt lies in the combination, where many partial observations are brought together into a fast judgment. That judgment is always made under uncertainty in the earliest phase. A very large offshore earthquake may rupture across a long stretch of plate boundary, and different parts of the rupture may unfold over many tens of seconds or longer. Early magnitude estimates can change as more data arrive. The location of stronger seafloor displacement may not match the first automatic solution. A tsunami may be larger in one coastal sector than in another because of details in seabed shape, rupture pattern, and coastal form. Observations indicate that rapid warning saves lives, especially when alerts are issued within moments. It remains uncertain in the first minutes exactly how large the final coastal effect will be in every location. This is why warnings are updated as the event develops, and why officials tend to prefer speed even when the earliest information is incomplete. The sea itself also alters how warning is understood. In deep offshore water, tsunami travels fast, crossing great distances with little loss of energy. Yet the wave remains difficult to judge by eye because its height can be modest far from shore. The danger becomes more apparent as the wave enters shallower water and its forward motion slows, causing energy to compress into greater height and stronger coastal flow. The offshore warning belt is therefore a race against geography. The farther a coastal community lies from the source, the more time warning may provide. The closer it lies, the more heavily safety depends on immediate automatic alerts and prior preparation. In nearby source regions, there may be only a brief interval between the earthquake and the arrival of dangerous water. For this reason, the offshore warning belt is not only a field of instruments, it is also a field of transmission. Signals must travel from sensor to analysis center, then outward to broadcasters, mobile networks, harbour authorities, trains, schools, factories, and households. A warning has value only when it moves quickly from data to decision. This practical chain must function during power loss, strong shaking, and public confusion. Its success depends on design long before any disaster begins. Engineers and emergency planners therefore treat offshore monitoring as part of a larger communication system rather than an isolated scientific task. From the shore, the open water may still appear silent and empty after an offshore earthquake. Nothing in the visible surface alone announces the complexity beneath. Yet this broad belt of sea is already active with detection, computation, and transmission. It is the first watched zone beyond the coast, where Japan reaches outward with instruments into the exposed Pacific margin. Here the country listens across the water for the earliest measurable signs that the seabed has shifted and that danger may be moving landward. The warning belt does not remove uncertainty, and it does not change the force of tectonic motion. It creates something more limited and more human. It creates a narrow margin of time, drawn from the open sea before the event reaches land. Far below the open water east and south of Japan, the floor of the sea bends into long and narrow depressions that mark one of the most important features in the earthquake story of the region. These are the great trenches and troughs, the outer scars of subduction where one tectonic plate begins to descend beneath another. At the surface, the ocean above them may appear little different from the surrounding Pacific. The waves pass overhead without revealing the full shape below. Yet on the seabed, the change is dramatic. The broad abyssal plain gives way to a steep descent, and the geometry of the margin becomes unmistakable. These long depressions are not small irregularities. They are major structures that define the boundary between moving plates and shape much of Japan's seismic hazard. To the northeast of Japan lies the Japan Trench, extending along the Pacific side of the main island arc. Farther north, related trench systems continue toward Hokkaido and the Kuril region. To the south, the Sagami Trough and the Nankai Trough trace important sections of the plate boundary nearer central and southwestern Japan. A trench is a deep linear depression on the ocean floor formed where an oceanic plate bends downward into the mantle. A trough in this setting is a similar large-scale depression, though the detailed structure and depth may vary. These names matter because they mark different segments of the broader plate boundary, each with its own geometry, history, and style of earthquake activity. Experts speak of them carefully because the location of strain storage and release is tied to these specific offshore structures. The sea floor approaching these trenches is not flat in any simple sense, but it is much smoother than the descending margin itself. As the oceanic plate nears Japan, it begins to flex downward. This bending can produce a broad arch farther seaward and then a sharper descent into the trench. Sediments cover parts of the floor, softening the visual impression, but the larger shape remains clear in bathymetric maps. Bathymetry is the measurement of water depth and the shape of the seabed. Through this mapping, the trenches appear as long dark ribbons cut into the ocean margin. They can extend for hundreds of kilometers, yet they are narrow compared with the width of the ocean basin behind them. Their scale is immense in human terms and precise in tectonic terms. They are the line where the oceanic plate presents itself for descent. The Japan Trench is especially well known because of its connection to some of the most powerful earthquakes and tsunamis ever recorded in the region. It lies east of northeastern Honshu, where the Pacific Plate moves beneath the plate carrying northern Japan. The trench marks the outer surface expression of this boundary. In maps and cross-sections, it appears as a deep notch parallel to the coast, separated from land by the forearc region, the belt of crust between the trench and the volcanic arc farther inland. In this outer layer of the story, what matters most is the shape itself. The trench is not merely a deep place in the sea. It is evidence of downward motion at the edge of a converging plate system. Farther south, the Sagami Trough lies closer to the densely occupied region around the Kanto area. Its form is influenced by the meeting of plate systems in a particularly complex part of Japan. Here the geometry is less simple than along some longer and more continuous trench segments. The trough still marks descent and convergence, but the structure is shaped by the intersection of multiple tectonic domains. This complexity is one reason the area draws such close scientific attention. The outer seabed form shows that the margin is not uniform from north to south. Even where the same broad process is present, the shape and arrangement of the boundary differ. Southwest of central Japan, the Nankai Trough extends offshore along the Pacific side of Shikoku and the Kii Peninsula toward Kyushu. It is shallower in appearance than some of the deeper trench systems to the northeast, yet it is no less significant. The oceanic plate approaching here carries sediments and irregular features on its upper surface, and the overriding margin has built a broad wedge of deformed material landward of the trough. The trough marks the beginning of descent, while the surrounding seabed records compression and scraping as the plates converge. In maps of the region, this margin appears as a long structural seam offshore from some of Japan's most heavily populated and industrially important districts. The great trenches and troughs do more than identify where plates meet. They also influence how scientists divide the plate boundary into segments for study. A segment is a portion of a larger fault or plate interface that may behave somewhat differently from neighbouring portions. Changes in trench orientation, depth, incoming seafloor topography, or sediment supply can all affect how the boundary is organised. The trench line, viewed from above, is therefore both a continuous feature and a set of distinct regions. This helps explain why earthquake concern is not distributed in a single uniform way along all of Japan's offshore margin. Each major trench or trough section has its own historical record, structural setting, and expected style of rupture. These depressions also matter because they are the first large-scale seabed forms involved in tsunami generation. When a major undersea earthquake shifts the plate boundary landward of the trench, the sea floor above the rupture may rise or fall. The trench itself is part of the geometry that shapes where this deformation occurs. The details of tsunami birth belong to later layers of the subject, but even here, at the level of seabed form, the connection is present. The great trench lines are not passive scars. They are active margins whose shape reflects ongoing tectonic motion and whose position frames the zone of potential seafloor displacement. Despite their importance, these features remain hidden from ordinary view. Satellites cannot see them directly through seawater in fine detail. Human beings do not stand beside them. Knowledge of them comes through sounding, mapping, seismic imaging, and long scientific effort. Yet once known, their significance is hard to overstate. They show where the Pacific and related oceanic plates begin their descent beneath Japan. They stretch for great distances parallel to the islands. They separate the open basin from the compressed margin. They give the offshore region its tectonic outline. In the calm language of geology, a trench or trough is simply a seafloor depression associated with subduction. In the broader reality of Japan, these structures are among the largest visible expressions of the forces that make experts wary. Their long lines on the seabed mark where motion is concentrated, where the ocean floor bends downward, and where strain begins to enter the plate boundary in a focused way. Here, beneath the open Pacific, the shape of the seabed itself declares that the region is not stable ground covered by water. It is a descending edge of the planet's outer shell. Landward of the great trenches and troughs, the seabed changes again. The dramatic drop of the trench is only one part of the offshore margin. Beyond it lies a broader and more textured zone, where layers of mud, sand, volcanic ash, and broken rock collect, shift, compress, and fold over long spans of time. This region does not attract as much public attention as the trench itself, yet it matters greatly in the science of major earthquakes. Here the surface of the ocean floor is softened by sediment, marked by ridges and basins, and shaped by the slow interaction between descending oceanic crust and the material scraped, bent, or carried along above it. The seabed in this belt is not a quiet covering placed over fixed rock. It is an active skin over a deforming margin. Sediment is loose material produced by erosion, volcanic activity, and biological remains, then carried by rivers, currents, and gravity into the sea. Around Japan, large volumes of sediment reach the offshore region from steep mountain slopes, short, fast rivers, and repeated volcanic processes. Some of it settles gradually through the water column. Some moves in pulses during storms, floods, or underwater slope failure. Over time it spreads across parts of the seafloor in sheets, fans, and uneven blankets. In some places these layers are thin. In others they grow thick enough to conceal the rougher shape of the older crust below. The result is a margin whose visible upper surface may appear smoother than the forces beneath would suggest. This sedimentary cover matters because the physical character of the plate boundary is affected by what lies above and upon it. A plate boundary is not always a clean rock surface pressing directly against another clean surface. It may be separated in part by fractured material, water-rich sediment, altered minerals, and broken blocks of crust. The thickness, water content, and strength of these materials can influence how strongly the two plates stick together. Friction, in simple terms, is the resistance to sliding between surfaces in contact. Along a plate boundary, friction helps determine whether stress builds for a long time in a locked state or is released more gradually. The seabed sediments above the boundary do not alone control this behavior, but they are part of the broader environment in which that behavior develops. The shape of the offshore floor also changes as sediment is compressed, where the incoming oceanic plate carries a cover of marine sediment toward the trench or trough. Some of that material is dragged downward with the plate, while some is scraped off and added to the edge of the overriding plate. This process can build a wedge of deformed sediment and rock landward of the trench. Layers that once settled flat on the seabed may become folded, faulted, and lifted into submarine ridges. Small basins may form between these rises and then fill with new sediment. The pattern becomes one of repeated rearrangement. From above, bathymetric maps show irregular bands and swells. From within the rocks, the story is one of compression, stacking, and slow displacement. Water plays an important role throughout this sediment-rich zone. Marine sediments often contain large amounts of pore water, the water held in the tiny spaces between grains. As sediment is buried and compressed, pressure within these pores can increase. High pore pressure can reduce the effective strength of the material, and alter how stress is transmitted through the margin. This does not mean that the margin becomes simple or weak in a uniform way. It means that the mechanical behavior of the boundary is shaped not only by solid rock, but also by the presence and movement of water within the sediment and fractures. Scientists study these conditions because they may help explain why some sections of a plate boundary rupture differently from others. The seafloor itself preserves traces of instability. Slopes built from soft or layered sediment can fail, especially when disturbed by shaking. Submarine landslides may occur on the continental slope or within the deforming wedge landward of the trench. These movements can reshape local seabed form and, in some cases, contribute to local sea disturbance. On the larger scale, however, the more important role of sediment lies in how it affects the geometry and material properties of the plate margin. A thick blanket of soft material is not merely decoration upon the crust. It changes weight, pressure, fluid movement, and the way strain may be distributed near the boundary. The incoming oceanic plate also carries its own roughness beneath the sediment cover. Buried volcanic highs, ridges, and fracture zones can approach the trench and pass beneath the overriding margin. Even when these features are partly hidden by sediment, they influence the shape of the seabed above and the contact below. Where rough topography enters the subduction zone, it may disturb the continuity of the plate interface, change local stress, or alter the thickness of sediment caught between the plates. Observations indicate that such irregularities can affect rupture behavior, though the precise effect differs from place to place and remains uncertain in many cases. The important point in this outer layer is that the seafloor is not a smooth and passive surface. It carries inherited structure toward the plate boundary. In the Nankai region, thick sediment has long been recognized as part of the offshore setting. This has helped produce a broad accretionary wedge, the mass of deformed sediment and crust added to the edge of the overriding plate. In northeastern Japan, different trench geometry and sediment conditions create a different offshore expression. These contrasts remind researchers that Japan's seismic margins are linked by the common process of subduction, but distinguished by local materials and forms. The seabed records these differences clearly. One segment may be deeply cut, relatively sediment-poor, and sharply defined. Another may be shallower in appearance, more thickly draped in sediment, and fronted by a wider zone of deformation. The quiet appearance of the sea surface above this region can hide these subtleties completely. Waves and weather tell little about the layers of fine mud, compacted sand, trapped water, and broken rock beneath. Yet these materials help shape the conditions under which large earthquakes begin and propagate. A rupture moving along a plate boundary does not pass through an abstract line on a diagram. It unfolds within a real physical setting made of rock, sediment, pressure, and fluid. The seabed and its cover therefore matter not only as scenery of the offshore margin, but as part of the mechanical system. In this region between trench and land, the ocean floor becomes a textured record of compression and accumulation. Sediment settles, shifts, and is deformed. Water remains within it under pressure. Ridges rise, basins collect more material, and irregular crust continues its slow approach from the open Pacific. This is the outer skin of the subduction zone, a layer that softens the boundary to the eye while adding complexity to its behavior. The more closely the margin is examined, the less it resembles a single clean break in rock. It appears instead as a layered and water-rich environment where the surface form of the seabed already reflects the deeper struggle of converging plates. Beneath the sedimented floor of the offshore margin, the moving structure of the earth becomes more direct. Here the descending oceanic plate approaches and enters the zone of subduction, the process in which one tectonic plate sinks beneath another into the deeper part of the planet. In the broad outer ocean, plate motion appears only as a matter of distant geography. At the trench and trough, it takes on a visible form in the shape of the seabed. In this deeper region, the motion becomes mechanical and intimate. Rock meets rock under enormous pressure. One plate bends downward, another is forced, lifted, and compressed above it. This is the plate margin in its essential working state, where slow motion over long time begins to store the conditions for sudden release. The oceanic plate arriving at Japan is old, cold, and dense compared with the hotter and more buoyant material beneath the overriding side of the margin. Density in this setting means the amount of mass within a given volume of rock. As oceanic crust ages after forming at a mid-ocean ridge, it cools and becomes denser. This makes it more likely to sink when it meets another plate. The downward path is not vertical. The plate bends and descends at an angle, carrying with it a layer of sediment, altered crust, and upper mantle rock. The angle differs from region to region, but the principle remains the same. The incoming slab is forced under the outer edge of Japan and continues downward over immense spans of time. Subduction is not a single line but a zone of interaction. The surface trace of that interaction appears at the trench or trough, yet the working boundary extends downward along the interface, where the two plates remain in contact. An interface is the surface between two different bodies or layers. In this case, it is the sloping contact where the top of the descending plate presses beneath the base of the overriding plate. That contact may remain mechanically connected over a broad area. It is along this buried surface that stress builds and, in some earthquakes, is released through sudden slip. To understand why experts worry about Japan's great earthquake zones, this buried interface is one of the most important places to examine. As the oceanic plate descends, it does not move freely like a smooth object sliding without resistance. The rocks on both sides are rough, fractured, altered by pressure and water, and pressed together with immense force. In some places the boundary may slide gradually. In others it may resist motion and remain stuck for long periods. Even when the relative movement of the plates continues overall, the local contact can hold fast. This means that motion expected from long-term plate convergence is not fully expressed as steady slip along the entire interface. Instead, part of that movement is stored as elastic strain in the surrounding rock. Elastic strain is the deformation that builds when material is bent or compressed, but has not yet broken or slipped. Over decades or centuries, this stored strain can become very large. The geometry of the descending plate matters greatly. As it bends into the subduction zone, the upper part of the slab remains close to the seabed near the trench, then passes deeper landward beneath the forearc region. The forearc is the part of the overriding plate located between the trench and the volcanic belt farther inland. Within this geometry, temperature, pressure, rock type, and fluid conditions all change with depth. These changes influence the mechanical character of the interface. Near the outer shallow margin, conditions differ from those at greater depth where the plate has descended farther and the surrounding rock is hotter and more compressed. Scientists map these variations because they help explain why some parts of the boundary may generate very large earthquakes while others tend to slip in quieter ways. Japan's setting is especially complex because several plate systems converge there. Along northeastern Japan, the Pacific plate descends beneath the plate carrying the island arc. Along the southern margin, the Philippine Sea plate descends beneath parts of southwestern and central Japan. These are not small motions. They are persistent regional processes that reshape the margin over millions of years, while also loading it with stress on human timescales. The details differ from one boundary to another, but both are forms of subduction, and both are capable of storing the energy associated with severe earthquakes and tsunami-generating rupture. In this region, experts do not worry because subduction is unusual. They worry because it is ongoing, measurable, and powerful. The contact between plates also affects the crust above. As the descending slab pushes under the overriding plate, the upper plate is shortened, thickened, and warped. Some of this deformation is slow and distributed. Some is focused on faults and folds. Yet the driving cause remains the same. Convergence at the plate boundary transmits force into the surrounding rock. The margin is therefore not a passive surface resting above a deep process. It is part of the process itself. The landforms and earthquake patterns observed in Japan are expressions of that continuing interaction below the offshore region. Water remains important even at this deeper layer. As the oceanic plate descends, minerals within the crust and upper mantle can release water under changing pressure and temperature. Some of this water may move upward into the overlying mantle wedge and crust. The mantle wedge is the part of the mantle located above the descending slab and below the overriding plate. Water can weaken certain minerals, promote melting at greater depth, and alter the frictional behavior of the boundary zone. At the level of the subduction interface, fluids can help control pressure within fractures and pores, changing how firmly the rocks press together in an effective mechanical sense. Observations indicate that fluid movement is an important part of subduction dynamics. It remains uncertain in many specific places exactly how fluid pressure changes through time, and how strongly those changes influence the timing of individual earthquakes. The descent of the plate is extremely slow by human standards, measured in centimeters per year, yet the accumulated effect is vast. A few centimeters each year becomes meters over a lifetime, and many tens of meters over historical intervals relevant to great earthquake cycles. Because the motion is steady while the boundary is partly locked, the strain budget of the region grows. This is one reason scientific concern remains persistent even during periods without a major event. The absence of recent rupture does not mean the process has paused. It means the plate may still be descending while parts of the interface continue to resist. Seen in cross-section, the subduction zone beneath Japan resembles a descending ramp of oceanic lithosphere passing beneath a compressed and fractured outer margin. Lithosphere is the rigid outer shell of Earth made of crust and uppermost mantle. This image is simple, but the reality is layered with variation. The slab may carry seamounts or rough crust into the boundary. The overlying plate may contain faults, sedimentary wedges, and stronger or weaker blocks of crust. The interface may change in behavior along its length and with depth, yet beneath all this variation, the main fact remains steady. One plate is going under another, and that movement is the engine of the region's greatest earthquakes. In this deeper region, the earthquake story becomes more than a matter of coastline, warning systems, trenches, or sediment. It becomes a story of converging slabs of the planet's outer shell, forced into contact over immense areas and immense spans of time. Subduction is the central mechanical act of the margin. It bends the incoming plate, loads the boundary, deforms the crust above, and creates the buried interface on which some of the most dangerous earthquakes can occur, here. Below the seabed and beneath the visible structures of the offshore Pacific, the concern of experts rests on a simple and powerful reality. The Earth under Japan is not still. It is in the act of descending. Along the buried surface where one plate passes beneath another, Movement is not uniform. The broad idea of subduction can suggest a simple steady slide, but the actual contact is divided into places that hold and places that move. This contrast is one of the most important features in the earthquake science of Japan. A section of the plate boundary may remain locked for many years, storing strain as the plates continue their larger motion. Nearby, another section may creep, meaning that it slips gradually without producing the same sudden release associated with a major earthquake. Between these two behaviors lies much of the uncertainty that experts study. The boundary is continuous in one sense, yet mechanically varied in another. It is this variation that shapes both long, quiet intervals and sudden destructive rupture. A locked zone is a portion of the plate interface where friction and pressure prevent smooth relative motion for an extended period. The plates continue to converge overall, but at that specific section of the boundary, they do not slide past each other as fast as the larger plate motion would require. Instead, the surrounding rock deforms elastically. The upper plate may be dragged seaward and downward near the margin, while regions farther inland are slowly compressed or tilted. These changes are extremely small from day to day, yet modern geodetic instruments can detect them. Geodesy is the science of measuring Earth's shape, size, and surface movement. Through dense networks of positioning stations, researchers can observe how the crust above a locked plate boundary gradually distorts. These measurements provide one of the clearest signs that motion is being stored rather than fully released. A creeping zone behaves differently. There, the interface slips more steadily, either continuously or in repeated small increments. Because some motion is accommodated without large sudden rupture, less elastic strain may accumulate in that exact portion of the boundary. This does not make the area irrelevant or safe in a simple way. Creep can alter the loading of neighbouring locked sections, and some forms of slow motion may occur near zones capable of large earthquakes. Still, the difference matters. Where the boundary creeps, the long-term accumulation of strain may be reduced compared with strongly locked sections. Where it locks, the potential for significant stored energy is greater. The distinction between locking and creeping is not always sharp. The boundary does not divide neatly into a few simple blocks. Instead, it may contain patches with different frictional properties, fluid conditions, temperatures, and rock structures. Some segments can be strongly locked at shallow depth, less locked farther down, and transitional in between. Others may remain mostly creeping but with isolated stuck patches. The result is a mechanical mosaic rather than a single uniform surface. This complexity helps explain why one earthquake may rupture across a wide area while another stops sooner than expected. It also helps explain why the history of great earthquakes along Japan's margin shows repetition without perfect regularity. One reason for this variation lies in the physical condition of the interface itself. Rock type influences strength. Water pressure in cracks and pores changes how tightly the surfaces are pressed together in an effective sense. Temperature alters mineral behavior and can change the way rock responds to stress. Roughness on the descending plate, such as buried ridges or volcanic highs, may create stronger sticking in some places or disrupt smooth contact in others. Sediment thickness also matters, as does the geometry of the boundary. None of these factors acts alone. Together they determine whether a portion of the interface will resist motion, slide quietly, or alternate between different modes over time. In Japan, careful measurement of crustal motion has shown that significant parts of the subduction boundary are strongly coupled. Coupling means the degree to which the two plates are mechanically linked and prevented from sliding freely. Strong coupling suggests a locked or mostly locked condition. Weak coupling suggests more continuous or episodic slip. This concept is central to expert concern, where coupling is high over a broad area. The long-term difference between actual slip and expected plate motion can become large. That difference is often called a slip deficit, meaning the amount of relative plate movement that has not yet been released at the boundary. Over decades, the deficit can grow until rupture becomes more likely, though the exact timing remains uncertain. Japan's offshore regions provide important examples of both concern and complexity. In the Nankai Trough, historical records and modern measurements indicate that major segments of the boundary can remain locked and then fail in large earthquakes separated by long intervals. In northeastern Japan, before the great rupture of the early 21st century, observations of crustal strain had already pointed to strong coupling along parts of the margin. Yet even when coupling is measured, uncertainty remains. A locked patch may fail alone or together with neighbouring patches. A creeping section may slow, accelerate, or help transfer stress to adjacent locked zones. The measured state of the boundary improves understanding, but it does not provide an exact clock. Slow slip events add another layer to this region. A slow slip event is a period during which part of the boundary moves over days, weeks, or months rather than in seconds. The motion may be too gradual to generate strong ordinary shaking, yet it can be large enough to detect with precise instruments. Some slow slip occurs deep on the interface. Some may occur nearer the trench in certain settings. These events are especially important because they show that the boundary can release energy in more than one way. They also demonstrate that the plate interface is active even during periods without a major earthquake. In some cases, slow slip may change stress on nearby locked zones. Observations indicate that such interaction can matter. It remains uncertain in many specific cases whether a given slow slip event increases or decreases the near-term likelihood of larger rupture nearby. The crust above a locked zone often carries the surface expression of the hidden strain. Coastal areas may rise or sink very slowly. Inland regions may shift by small amounts measured over years. These movements are not dramatic enough to shape daily experience, but they are part of the quiet loading phase of the earthquake cycle. In contrast, when a locked section finally fails, the stored deformation is released abruptly. Land may rebound, the seafloor may move. Stress is redistributed across the region. Thus, the distinction between locked and creeping behaviour is not an abstract classification. It determines whether motion is expressed gradually and quietly or delayed until a violent change. Experts remain especially cautious because locking can persist for long periods without obvious surface warning. A community may live for generations above a segment that is steadily accumulating strain, while everyday life continues without unusual signs. Instruments can reveal the hidden process, but human intuition alone cannot. This is one reason earthquake science in Japan depends so strongly on long-term monitoring. The boundary must be observed patiently, because the most dangerous sections may appear outwardly calm while they are storing the conditions for future rupture. At this level of the subject, the plate margin becomes less like a single descending surface and more like a varied mechanical landscape. Some portions hold fast, some move slowly, some alternate between relative quiet and subtle release. The contrast between locked and creeping zones explains why earthquake danger is concentrated unevenly and why exact prediction remains so difficult. It also explains why expert concern is steady rather than dramatic. The boundary does not need to show obvious turmoil at every moment. Its quietest sections may be the ones storing the greatest strain. Waiting within the dark contact between plates beneath Japan's offshore margin, above the locked and creeping boundary, The overriding crust carries the slow burden of stored tectonic force. This crust is the upper body of rock that forms the outer frame of Japan above the descending plate. It does not simply rest upon the subduction zone like a quiet cover over machinery. It bends, tightens, lifts, and settles in response to the hidden contact below. These changes are often too small to notice without instruments, yet they are central to the earthquake cycle. When experts speak about strain building through time, much of what they mean is happening here in the upper plate, where rock is deformed over years, decades, and centuries as motion continues below, but is not fully released along the buried interface. Strain is the change in shape or size that occurs when material is stressed. In rock, strain may appear as bending, shortening, stretching, tilting, or gradual displacement along faults. In the overriding crust above Japan's subduction zones, the most important long-term pattern is compression and warping caused by convergence at the plate boundary. When the interface remains locked, the descending plate keeps moving relative to the overriding plate, but the contact resists smooth slip. The upper crust is then dragged and distorted. Coastal regions near the margin may slowly shift seaward or downward. Areas farther inland may be compressed, uplifted, or slightly rotated. These changes are not random. They are part of a broad elastic response to the stored motion. Elastic deformation means that rock changes shape under stress in a way that can be partly recovered when the stress is suddenly released. This idea is fundamental to large earthquakes. The crust above a locked boundary behaves in some respects like a body under tension that is slowly bent from its preferred form. The bending is small compared with the total thickness of the crust, but over large distances it becomes measurable. After a major earthquake, when the locked section suddenly slips, parts of the crust may rebound, shifting in the opposite direction from their earlier slow deformation. The surface movement seen in such moments is therefore not separate from the quiet years before the rupture. It is the abrupt release of strain that has long been stored in the upper plate. Japan provides unusually clear evidence of this slow loading, because it is observed by dense geodetic networks. Stations fixed across the islands record tiny motions of the land relative to one another. These motions reveal that the crust is not still between earthquakes. It is moving continuously in patterns that reflect the degree of coupling on the plate boundary offshore. In some regions, the land is drawn toward the trench, while also being compressed inland. In others, the pattern is more complex, shaped by fault zones, crustal blocks, and variable coupling at depth. Even where the details differ, the main lesson remains steady. The overriding crust registers the hidden state of the subduction interface. This crust is not a single uniform shell. It contains mountain belts, sedimentary basins, volcanic regions, old fault systems, and blocks of rock with different strengths and histories. A basin is a broad low area where sediment accumulates. A fault is a fracture in rock along which movement has occurred. These internal differences matter because stress entering the upper plate does not spread through perfectly even material. Some structures may absorb deformation gradually. Others may concentrate it. Old faults may be reactivated under new stress conditions. Sedimentary basins may sink slowly or amplify later shaking because of their softer fill. Mountain belts may rise through long compression. The crust above the subduction zone is therefore a varied medium through which the effects of plate locking are filtered. Along parts of Japan's Pacific margin, coastal terraces and uplifted marine deposits preserve longer records of crustal movement over many earthquake cycles. A marine terrace is a former shoreline or wave-cut surface raised above present sea level by uplift. These landforms show that the outer crust does not merely flex once and return to its former state in a perfect repeat. Over long spans of time, repeated cycles of loading and release, combined with permanent deformation, can build lasting changes into the landscape. In some places the land rises overall, in others subsidence. The gradual sinking of the ground may dominate for periods of time. These patterns depend on local structure, the geometry of rupture, and the balance between sudden earthquake displacement and slower interseismic deformation. Interseismic means the period between earthquakes. Within the crust, faults above the main plate boundary can also become part of the stored strain system. Not all damaging earthquakes in Japan occur directly on the plate interface. Some happen within the overriding plate itself, where stress transferred from the subduction process acts on crustal faults closer to the surface. These shallower crustal earthquakes may affect smaller areas than a great offshore rupture, but they can still be severe because they occur near populated regions. Their existence shows that the upper plate is not only a passive recorder of deeper motion, it is an active region where stress can build and be released on its own faults as part of the larger tectonic setting. The deformation of the overriding crust also influences the seafloor above the offshore boundary. If the outer margin is slowly dragged downward during a locked phase, then released upward during rupture, the sudden change can contribute to tsunami generation. This means the crust stores not only the potential for shaking on land, but also part of the vertical motion that affects the sea above. The shape of coastal uplift or subsidence after an earthquake often reveals how the upper plate had been strained beforehand. Observations after major events in Japan have shown coastlines locally rising in some places and sinking in others, a pattern that reflects the geometry of strain release across the crustal block above the fault. Experts are careful not to describe this process as a simple countdown. The presence of strain does not mean that the exact time of rupture can be known. The crust may hold stress longer than expected, or deformation may be redistributed by slow slip, smaller earthquakes, or changes in neighboring segments. Still, the persistent observation of crustal strain is one of the strongest reasons for concern. It shows that tectonic force is not hypothetical. It is measurable in the land itself. The ground beneath towns, rivers, plains, and mountains is gradually changing shape under the influence of the locked boundary offshore. At the human scale, this loading phase is nearly silent. Roads remain in place, buildings stand, daily life proceeds. Yet beneath this quiet surface, the crust of the upper plate is carrying an accumulating imbalance between the steady motion of the plates and the incomplete release of that motion at depth. The imbalance is written into subtle shifts of elevation, horizontal displacement, and stress on faults. Over time, it turns the overriding crust into a reservoir of elastic energy. When the boundary slips, some of that stored distortion is released in moments. In this region above the interface, the earthquake story becomes a story of hidden shape change. The overriding crust bends under force, stores strain, and transmits stress through a varied body of rock that includes faults, basins, and rising terrain. It preserves the quiet phase of the cycle between great ruptures and helps determine how that rupture will later affect land and sea. Here the concern of experts rests on a simple observation made with great precision. The crust above Japan's subduction zones is not waiting in stillness. It is slowly changing form under pressure, carrying within it the physical memory of motion that has not yet been released. The record of past earthquakes around Japan lies partly in written history, partly in instrumental measurement, and partly in the altered land and sea themselves. When experts look backward through these layers, they do not search for a perfect script of the future. They look instead for patterns, limits, and recurring forms of rupture that help define what is possible and what remains uncertain. Past earthquakes matter because they reveal how the plate boundary has behaved across different segments and over different spans of time. They show repetition, but not exact repetition. They show order in the broad sense, yet irregularity in the details. In the historical layer of the subject, the science becomes a patient reading of earlier releases of strain. Japan's long-written record gives unusual depth to this effort. Court chronicles, temple documents, regional archives, official reports, and later newspapers preserve observations of strong shaking, coastal flooding, ground change, fire, landslide, and social disruption. These accounts vary in reliability and detail. Some are sparse and local, others are broad and descriptive. Together they form a historical catalogue that extends farther back than the instrumental era. This matters because great earthquakes along subduction zones often recur over intervals longer than a human lifetime. Without historical records, many important events would remain outside direct memory. With them, scientists can compare centuries rather than decades and recognize that severe offshore earthquakes have returned more than once to the same general margins. Along the Nankai Trough, the historical sequence is one of the clearest examples. Large earthquakes of about magnitude 8 or greater have occurred there repeatedly over the centuries, often with intervals on the order of 100 to 150 years. Though the spacing is not exact and the rupture areas are not always identical, some events appear to have broken a very large extent of the trough in a single sequence. Others occurred as paired ruptures separated by hours, days, or even a few years. The historical earthquakes of the 19th and 20th centuries provide especially important examples because they are better documented than older events. The pattern suggests that the Nankai margin can fail in more than one way. It can rupture broadly or in linked but staggered segments. This is one reason experts remain cautious. The past offers a family of behaviours rather than one fixed model. The 20th century sequence along the Nankai margin is often studied closely for this reason. In the middle of that century, one large rupture occurred in the eastern part of the trough, followed about 2 years later by another large rupture farther west. This does not prove that the same delay must happen again, nor does it require that future events unfold in that order. It shows instead that adjacent segments can fail separately within a short historical interval. Earlier centuries also record major Nankai earthquakes, including events interpreted as involving broad and destructive rupture. The lesson is not a precise timetable. The lesson is that the margin has a demonstrated capacity for repeated great earthquakes with variation in timing and extent. Northeastern Japan offers a different but equally important historical lesson, offshore east of Honshu. The subduction boundary has produced both large historical earthquakes and, in the early 21st century, one of the most powerful earthquakes ever instrumentally recorded. That event revealed that the plate interface near the trench could rupture far more extensively than many prior hazard assumptions had allowed. Instruments showed immense slip on the shallow megathrust, widespread crustal deformation, and tsunami generation on a devastating scale. In the years before that rupture, scientists already recognized the northeastern margin as hazardous and strongly coupled in places, yet the full size and shallow concentration of slip still exceeded many expectations. This is one of the strongest lessons from the historical and instrumental record combined. Even in a highly studied region, the upper limit of rupture behavior may be revised by a single event. The value of the instrumental era lies in its precision. Since the 20th century, seismographs, tide gauges, sea level records, geodetic networks, and later satellite-based measurements have transformed the earthquake record from narrative description into quantitative observation. Magnitude can be estimated more consistently. Rupture extent can be reconstructed. Aftershocks can be mapped. Tsunami heights can be measured across many coasts. Surface displacement can be compared with deformation models. This does not remove uncertainty, but it sharpens the view. Historical accounts may tell that the sea withdrew and returned with force. Instruments can add the timing, amplitude, direction, and relation to fault motion. Together, old and new records create a much fuller archive than either could provide alone. Paleoseismology extends the record still farther back. Paleoseismology is the study of prehistoric earthquakes using geological evidence such as tsunami deposits, uplifted shorelines, drowned marshes, and disturbed sediment layers. In coastal plains and lowlands of Japan, researchers have found sands carried inland by earlier tsunamis and buried within quieter deposits. In some places, these layers suggest large events older than written history. Such findings are especially important where the historical record is short or incomplete. They show that the earthquake cycle can be longer than the documentary archive, and that unusual-looking events in modern times may still have deeper precedents in the geological past. Yet the record also teaches restraint. Repetition does not mean strict regularity. Similar margins can produce different rupture patterns in different centuries. Segments thought to be separate may join. Segments expected to rupture together may remain partly independent. Magnitude estimates for older events often carry uncertainty because reports are incomplete and indirect. Tsunami deposits may indicate a large marine inundation without yielding a simple one-to-one measure of earthquake size. Even in the instrumental era, interpretation evolves as methods improve. Scientists therefore use the past as a guide, not as a script. Another lesson concerns clustering and sequence. Some earthquakes redistribute stress in ways that appear to increase loading on neighboring segments. Others may release strain over a broader area than anticipated. After a great rupture, aftershock sequences and post-seismic deformation continue for years, complicating the pattern of future hazard. Post-seismic means occurring after the main earthquake as the crust and mantle continue to adjust. This reminds experts that a major event is not a single isolated moment in the record. It is part of a longer arc of deformation before and after the main rupture. The historical catalogue must therefore be read not only as a list of dates, but as an evolving system of connected releases. The deeper meaning of these past ruptures is sober and cumulative. Japan's earthquake history shows that great subduction earthquakes are not rare anomalies imposed from outside ordinary experience. They are recurring expressions of the plate boundary beneath the country. The exact dates, sizes, and combinations vary. The long-term reality does not. This is why experts study old chronicles, modern seismograms, seabed deformation, and buried tsunami sands with such care. Each layer of evidence narrows some uncertainties while leaving others open. Together they show what the margins have done before, what they are capable of doing again, and why concern remains grounded not in imagination, but in the repeated physical history of the region. After a major earthquake, attention often turns towards signs that seem to point ahead. Small shocks cluster near the source region. Instruments detect further motion on the fault. The crust continues to adjust. People ask whether a larger event may follow, whether the worst is over, and whether the sequence itself is changing shape. In this region of the subject, the science becomes careful and restrained. Earthquakes do not usually announce themselves in a clear and reliable way before they happen. Yet the period before and after a large rupture is not empty of information. It contains signals, but these signals are uneven, incomplete, and difficult to interpret with certainty. Experts study them closely because they reveal how the system is evolving, not because they offer exact prediction. The most familiar signal is the foreshock. A foreshock is an earthquake that occurs before a larger earthquake in the same area and is recognized as such only after the larger event has happened. This definition matters. A small or moderate earthquake is not known in advance to be a foreshock. At the moment it occurs, it may appear to be an ordinary event or even the main shock of its own sequence. Only later, if a larger rupture follows nearby, does the earlier event receive the label. This is one reason prediction remains so difficult. The same type of earthquake may, in one case, remain the largest event in the sequence, and in another case become only the beginning of something greater. Japan's earthquake history includes important examples of this uncertainty. Some large offshore events have been preceded by smaller but still powerful shocks. In hindsight, those earlier events can look like warnings. In real time, however, the situation is less clear. Many earthquakes are followed only by smaller aftershocks. Only a minority are followed by a larger rupture. This means that the presence of a preceding shock can raise concern without providing certainty. Experts treat such patterns seriously, especially in known high-risk regions, but they do not present them as dependable short-term predictions. Observations indicate that certain earthquake sequences may involve foreshock activity. It remains uncertain before the fact whether any given shock is the beginning of a larger cascade. Aftershocks are more common and better understood in a statistical sense. An aftershock is an earthquake that follows the main rupture in the same general region as the crust adjusts to the new distribution of stress. Aftershocks tend to be most frequent soon after the main shock and then gradually decline over time, though the exact pattern varies. Larger earthquakes typically produce more aftershocks than smaller ones. Some aftershocks can themselves be strong enough to damage buildings already weakened by the main event, trigger landslides, or disturb recovery work. This is why experts continue to warn about danger even after the first major shock has passed. The ground may remain active for days, weeks, months, or longer. Statistical aftershock forecasting is possible in a limited way. By studying the behavior of past sequences, scientists can estimate the probability of further earthquakes above certain magnitudes in the hours, days, or weeks after a main shock. These estimates are useful for emergency response because they help authorities judge continuing risk. Yet they are not predictions in the ordinary sense. They do not identify the exact time, place, or size of the next shock. They describe likelihood based on patterns observed in many earlier sequences. This is an important distinction. Science can estimate changing probability after a large earthquake. It cannot provide precise short-term certainty, along subduction zones such as those near Japan. Another important signal is slow slip. A slow slip event is a period during which part of the plate boundary moves gradually over days to months without producing the abrupt, strong shaking of an ordinary earthquake. The total amount of motion can be significant even though it is spread over time. Such events are detected through precise measurements of crustal movement, and sometimes through related tremor, a weak seismic signal generated by slow fault motion at depth. Slow slip does not always occur near the same parts of the boundary as major ruptures, and its meaning is not always the same from one region to another. Still, it shows that the plate boundary remains active even when no major earthquake is visible at the surface. In the Nankai region especially, slow slip has drawn sustained scientific attention. Repeated observations indicate that parts of the plate boundary there undergo slow movement during periods that otherwise seem quiet. These changes are interpreted as signs that the coupling condition of the boundary is not fixed. Coupling, in this setting, refers to how strongly the plates are locked together. A change in coupling may alter the distribution of stress along neighbouring sections. This does not mean that every slow slip event points directly toward a major earthquake. It means that the state of the boundary is dynamic, and that slow processes may matter in the long preparation phase of a future rupture. Experts watch these events because they offer rare clues about ongoing fault behaviour within otherwise hidden regions. Crustal motion after a major earthquake also continues in ways that may not be immediately obvious. The surface may keep shifting for months or years through post-seismic deformation, the gradual adjustment that follows the main rupture. Some of this adjustment comes from afterslip, which is continued fault movement around the edges of the main rupture zone. Some comes from slower flow in deeper hot rock beneath the crust. Together, these processes reshape stress in the surrounding region. They can load some areas while easing stress in others. For this reason, the end of strong shaking does not mark the end of tectonic change. The Earth continues to settle into a new state, and that settling can influence later seismic activity. Despite all these signals, the central scientific limit remains firm. No method has been shown to predict a major earthquake with consistent reliability in the short term. Swarms of small earthquakes may fade without consequence. Foreshock-like sequences may stop. Slow slip may occur without immediate rupture. Groundwater changes, electromagnetic effects, and other proposed precursors have been investigated for many years. Yet none has provided a universal and dependable warning method. This does not make observation useless. It clarifies what observation can and cannot do. It can reveal changing conditions, update probabilities, and improve understanding of fault processes. It cannot announce with certainty that a particular large earthquake will occur tomorrow or next week. This measured position can seem unsatisfying, especially after a frightening event. Yet it is one of the most honest parts of earthquake science. Experts do not ignore signals. They examine them carefully, compare them with long records, and issue guidance where justified. At the same time, they avoid turning ambiguous patterns into false confidence. In Japan, where monitoring is dense and the plate boundary is studied with exceptional care, this restraint is especially meaningful. If exact short-term prediction were available, it would likely have emerged here. Instead, what has emerged is a more realistic picture of an active system that sometimes offers hints, often remains ambiguous, and always requires humility. In this region of the story, the boundary between knowledge and uncertainty is clear. Foreshocks, aftershocks, slow slip, tremor, and post-seismic adjustment all reveal that a major earthquake is not a single isolated instant. It is part of a larger sequence of changing motion before and after rupture. These signals help experts track that sequence and judge evolving risk. They also show why concern can persist even when prediction remains limited. The Earth around Japan does speak through its smaller motions and slower changes. It simply does not speak in a language clear enough to tell the exact future. A large earthquake does not end at the edges of its first rupture in any simple way. When one section of a plate boundary suddenly slips, the surrounding crust and adjacent fault segments do not remain untouched. Stress is redistributed across the region. Some areas are relieved, others are loaded more strongly. This is why experts speak carefully about cascading failure, a phrase that describes the possibility that one rupture may alter conditions enough to encourage further rupture nearby. In Japan, where long subduction margins are divided into partly connected segments, This problem carries unusual weight. The concern is not that every earthquake must trigger another great one. The concern is that the plate boundary is a linked mechanical system, and change in one part can matter for the others. Stress transfer is the movement or redistribution of tectonic force after an earthquake changes the shape of the crust. When a fault slips, the surrounding rock adjusts. Some neighbouring areas may become less likely to fail immediately because part of the stored force has been released there. Other areas may be pushed closer to failure because the new pattern of strain increases the load placed upon them. This principle is well established in earthquake science. Though its exact effects are difficult to calculate in detail for any one future event, the Earth is not a set of smooth ideal blocks. Real faults are rough, layered, fluid-rich, and irregular. Even so, the broad principle remains. A major rupture can disturb the balance on neighbouring sections, and that disturbance may matter over timescales ranging from minutes to years. Along Japan's subduction margins, the possibility of linked behaviour is especially important because the plate boundary is long and segmented, rather than uniformly locked from end to end. A segment is a portion of the boundary that has its own geometry and mechanical character, even while remaining connected to adjacent portions. Historical records from the Nankai Trough show that great earthquakes there have sometimes involved nearly the full expected source region, while at other times the eastern and western halves have ruptured separately with a time gap between them. Japan Meteorological Agency describes this pattern directly, noting that past Nankai earthquakes have occurred across almost the whole source region at once in some cases, while in other cases a large earthquake struck one half and a second large earthquake followed later in the other half. This historical behaviour is one reason the Nankai Trough remains a focus of sustained concern. The margin extends from Suruga Bay toward offshore Hyuga-Nada and is capable of earthquakes of magnitude 8 or greater. Official Japanese sources emphasize that these earthquakes recur on the order of roughly 100 to 150 years, while also stressing that the exact repetition interval, source area, timing, and scale vary. That combination is crucial. The long-term pattern shows that the boundary repeatedly stores enough strain for very large rupture. The irregularity shows that rupture does not follow a fixed schedule or a single uniform path. Because of that irregularity, one major event along the trough would immediately raise scientific concern about how the remaining segments have been affected. The phrase cascading failure can sound dramatic, but in geology it refers to a sober mechanical possibility. If one segment fails, the change in stress may advance failure on an adjacent segment that was already close to slipping. The second rupture might follow quickly, after hours or days, or only after a longer period of adjustment. It might also fail to occur at all. This uncertainty is central. Scientists can identify the physical basis for linked rupture, and history shows that separated segments can rupture in close succession. What they cannot do with confidence is say, in the immediate aftermath of one event, exactly whether the next segment will fail, when it would fail, or how far the chain would continue. This is why post-earthquake evaluation becomes so careful after a major subduction event. Seismologists map aftershocks, geodesists measure crustal movement, and modelers estimate how stress has changed around the rupture zone. They look for whether neighbouring locked sections may have been loaded, whether slow slip has begun on nearby parts of the interface, and whether the event has altered the likelihood of another large shock. These assessments are useful, but they remain probabilistic rather than exact. The Earth does not reveal a simple threshold beyond which a second major rupture becomes certain. What it offers instead is a changed field of stress that may increase or decrease hazard in different places at once. The coastal consequences make this problem even more serious. If one segment of a subduction zone ruptures, the first disaster may already involve strong shaking, tsunami, infrastructure damage, and widespread social disruption. A second large rupture affecting a neighbouring segment could then strike a region that is already strained by emergency response, damaged transport, and public anxiety. This is one reason Japanese authorities have developed special frameworks for anomalous phenomena along the Nankai Trough and for temporary information released when unusual seismic activity raises concern. These systems do not claim that a second great earthquake can be predicted with precision. They exist because the historical record and the mechanical understanding of the trough both show that one major event does not always end the sequence. Linked rupture also matters in a broader scientific sense because it reveals that the plate boundary cannot be understood only as separate local sources. Each segment has its own properties, but no segment is fully isolated. The shape of the subducting plate, the distribution of fluids, the roughness of the interface, and the pattern of locking all influence how far rupture may spread and where it may stop. A boundary may resist propagation at one bend or transition, then allow it across another. In some cases, what had seemed like separate sections in one historical period may behave as a more continuous rupture zone in another. This is one lesson learned from very large subduction earthquakes worldwide and from the re-evaluation of hazard assumptions after unexpectedly broad ruptures. Experts therefore remain measured in their language. They do not say that every Japanese earthquake is the start of a chain. They do not say that one rupture guarantees another. They say instead that the physical conditions for cascading behavior exist, that Japan's historical record shows examples of large events occurring across different segments in close succession, and that this possibility must be built into planning and interpretation. The concern is grounded not in alarm but in structure. A long subduction margin stores strain in connected pieces. When one piece gives way, the rest of the system must be examined anew. In this region of the story, the earthquake hazard becomes less like a single point of failure and more like a tensioned chain beneath the seabed. One link may break alone, several may break together, one may weaken the next without immediately triggering it. The outcome cannot be known with certainty in advance, yet the principle is clear. Large ruptures change the state of the faults around them, and those changes can matter profoundly in a country built above long, segmented, and heavily studied plate boundaries. This is why experts watch not only the first great break, but the altered system that remains after it, quiet on the surface, still deciding how much of its stored force has truly been released. When a great offshore earthquake shifts the sea floor, the water above it responds at once. The motion is not like the ordinary rise and fall of wind-driven waves. It begins instead with a sudden displacement of a large part of the water column from below. If the seabed is lifted, the water above is lifted with it. If the seabed drops, the water surface above is drawn downward. Gravity then acts to restore balance, and that effort to regain balance sends energy outward across the sea in long waves. This is the birth of a tsunami, a wave train generated mainly by abrupt vertical movement of the ocean floor during an undersea earthquake in the waters around Japan, where major subduction zones lie close to inhabited coasts. This process is one of the most serious links between deep tectonic motion and surface disaster. The first step is displacement along the rupturing plate boundary. One section of the sea floor may rise by several meters while another section sinks. The total area involved can be immense, stretching over many tens or even hundreds of kilometers, because the water is already resting under gravity across that moving floor. It cannot remain still when the boundary shifts beneath it. the disturbance is transmitted through the full depth of the water column. This is one of the key differences between tsunami and ordinary surface waves. Wind waves affect mainly the upper part of the sea and are shaped by local weather. A tsunami involves the entire depth from seafloor to surface, which is why it can carry such large amounts of energy across long distances. In deep offshore water, the form of the wave is often deceptive. The wavelength, the distance from one crest to the next, can be extremely long, sometimes on the order of many tens or hundreds of kilometers. The height in the open ocean may remain modest, often much smaller than the later wave near the coast. A ship far from land may pass over the wave with little sign of danger. The sea surface may rise and fall slowly rather than breaking in a dramatic crest. Yet the wave is moving fast and carrying energy across a broad front. The speed depends largely on water depth. In very deep water, tsunami can travel with the pace of a fast aircraft, though the exact speed changes with local depth. Around Japan, where trenches and deep basins lie not far from shore, this rapid travel leaves little time between source and impact for many coastal communities. The direction of travel is shaped by the source and by the sea floor. A tsunami does not move outward in one simple ring like a perfect ripple on a pond. The pattern depends on where the rupture occurs, how the seabed is displaced, and how the surrounding bathymetry guides the wave. Bathymetry is the shape and depth of the seabed, ridges, slopes, basins, and bends in the continental margin can redirect energy, focus it, or spread it more widely. A section of coast lying to one side of the rupture may receive less energy than another section farther away, but more directly aligned with the strongest wave path. This is one reason why tsunami effects often differ sharply from place to place. The source may be single, but the consequences are uneven. As the wave approaches shallower water, its behavior changes. The sea floor rises toward the coast, and the lower part of the wave begins to interact more strongly with the bottom. This slows the forward speed, yet the energy remains, and as the wave slows, its length shortens and its height tends to increase. This process is often called shoaling, the transformation of a wave as it enters shallower water. The surface that seemed gentle in deep water may now rise more steeply. The front of the wave may compress, and the water behind it may pile upward. At this stage, the tsunami becomes far more dangerous to coastal settlements, ports, river mouths, and low plains. The first sign at the shore is not always a great wall of water. In some cases, the sea first draws back unusually far, exposing the seabed, harbour floor, or coastal shallows. In other cases, the first arrival is a rapid surge inward, with little preceding retreat. This depends on whether the first phase of the arriving wave is a trough or a crest, and on the local shape of the coast. For this reason, people living near tsunami-prone coasts are taught not to depend on any single visual pattern. Strong or long shaking near the shore is itself enough reason to move quickly to higher ground. The sea may retreat, or it may not. The danger exists either way. Once the wave enters bays, inlets, estuaries, and coastal plains, local geography becomes decisive. A narrow bay can funnel water inward and amplify the rise. A broad low plain can allow the wave to travel far inland as a fast-moving flood. A river mouth can carry the surge upstream beyond the immediate coast. Harbour walls and breakwaters may alter local flow, but they cannot remove the underlying force if the event exceeds their design conditions. In some places, the greatest danger comes from depth. In others, it comes from velocity, the speed of the water as it pushes across the land. Even relatively modest depth can become lethal when water moves with great force, carrying debris, overturning vehicles, battering structures, and eroding foundations. A tsunami also arrives as a sequence rather than a single isolated wave. The first wave is not always the largest. Later surges may be higher or may coincide with tidal conditions that worsen flooding. The interval between waves can be long enough to mislead those who believe the danger has passed. This repeated arrival is one reason coastal warnings remain in effect well after the first inundation. Water may continue to surge, recede, and return over many hours. Harbours are especially vulnerable to these repeated currents, which can tear vessels from moorings, damage quays, and produce dangerous oscillations within enclosed basins. The height reached on shore depends not only on the wave itself but on the land it meets. Steep coasts may force water upward over a shorter distance. Flat coasts may allow deep inland penetration. Local embayments can resonate, meaning that the incoming wave motion matches the natural oscillation of the basin and increases water movement. Small differences in seafloor contours, coastal slope, and built structures can therefore produce large differences in outcome over short distances. This explains why tsunami maps are developed with such care and why historical flood marks remain so important. The water does not spread evenly, it follows shape. In Japan, the closeness of major subduction sources to populated coasts makes this whole sequence unusually compressed. A seabed rupture begins in the dark below the ocean floor. Within moments, the water above is displaced. Within minutes, the long wave is travelling across deep sea. Soon after, depending on distance from the source, the wave begins its transformation over shallower margins and enters the complicated geometry of the coast. By the time it reaches land, the original tectonic motion is no longer visible as fault slip. It has become moving water, carrying the energy of the earthquake into towns, fields, roads, rivers, and harbours. This is the inner logic of tsunami birth and travel. The sea does not act independently of the earthquake. It receives the motion from the deforming seabed, transmits it across the full depth of the ocean, reshapes it over the continental margin, and delivers it to the coast according to the contours of the land and the sea floor. What begins as a sudden shift along the plate boundary becomes, through gravity and water, a travelling force that can cross great distances and then concentrate with terrible efficiency near shore, in the waters around Japan. This process remains one of the clearest reasons why offshore earthquakes are feared not only for the shaking they produce, but for the sea they set in motion. When seismic waves leave the deep plate boundary and enter the crust beneath Japan, they begin a complex journey through rock that varies in thickness, composition, and structure. These waves carry the energy released by sudden fault movement and transmit it toward the surface, where people experience shaking. The strength and duration of that shaking do not depend only on the size of the earthquake. They depend also on how the waves travel through the ground and how different geological settings respond to their passage. In this region, the science moves from the deep interface to the behavior of waves within the upper crust and the surface layers that cover it. Seismic waves are the vibrations that move outward from an earthquake source. There are several types, but the most important distinction at this level is between waves that travel through the interior of the earth and those that move along or near the surface. Interior waves pass through rock in different ways, compressing and shearing it as they go. Surface waves travel along the outer layers and often produce the strongest ground motion felt at a distance. As these waves approach Japan's landmass, they encounter a crust that is far from uniform. Mountains, basins, volcanic regions, and sediment-filled plains all respond differently, shaping the final pattern of shaking. In mountainous regions, where bedrock lies closer to the surface, seismic waves may pass more directly through relatively solid material. This can produce strong but often shorter duration shaking compared with softer regions. The rock transmits energy efficiently, but it does not trap the waves for long. In contrast, sedimentary basins, where thick layers of softer material fill low-lying areas, can significantly modify wave behavior. These sediments may be composed of sand, clay, and other deposits laid down over long periods. When seismic waves enter such a basin, they slow down because the material is less rigid than solid rock. As the waves slow, their energy can become concentrated, increasing the amplitude of motion. This amplification effect is one reason why cities built on soft ground may experience stronger shaking than nearby areas on firmer rock. The waves can also become trapped within the basin, reflecting off boundaries between layers and prolonging the motion. This leads to longer shaking durations, which can increase the likelihood of structural damage. The effect is not uniform across the basin. Differences in depth, layering, and geometry create zones of stronger or weaker motion. Even within a single city, shaking intensity may vary from one district to another depending on local ground conditions. Another important factor is resonance. Resonance occurs when the natural frequency of the ground or a structure matches the frequency of the incoming seismic waves. When this happens, motion can be amplified further. In sedimentary basins, certain wave frequencies may be enhanced, affecting buildings that are sensitive to those frequencies. Taller structures tend to respond more strongly to longer period waves, while shorter buildings respond to shorter period waves. The interaction between ground motion and built structures becomes especially important in densely populated regions such as Tokyo, Osaka, and other major urban areas in Japan. The path taken by seismic waves also matters. As waves travel outward from the source, they may pass through regions of different rock types, temperatures, and fault structures. Each transition can refract or reflect part of the energy, altering its direction and strength. Some paths allow waves to travel efficiently over long distances with relatively little loss. Others scatter the energy, reducing its intensity before it reaches the surface. In Japan, the complex tectonic setting means that wave paths are rarely simple. The interaction between subducting slabs, volcanic arcs, and crustal blocks creates a varied medium through which seismic energy must pass. In addition to these natural factors, the depth of the earthquake plays a role. Shallow earthquakes tend to produce stronger surface shaking because the energy has less distance to travel before reaching the ground. Deeper earthquakes may be felt over a wider area, but often produce less intense shaking at any single location. However, this general pattern can be modified by local geology. A shallow earthquake beneath soft sediment can produce severe shaking, while a deeper event beneath more rigid rock may be less damaging locally. Japan's extensive monitoring networks provide detailed observations of how these factors combine in real events. Seismometers distributed across the country record ground motion with high precision, allowing scientists to map shaking intensity and compare it with geological conditions. These data have shown clearly that local site effects, the influence of specific ground conditions at a location, are critical in determining damage patterns. Two areas at similar distances from an earthquake can experience very different levels of shaking due to differences in soil type, basin structure, and underlying rock. The behavior of seismic waves also influences secondary hazards. Strong shaking can trigger landslides in steep terrain, especially where slopes are weakened by weathering or previous disturbance. In low-lying areas with water-saturated sediment, shaking can cause liquefaction, where the ground temporarily loses strength and behaves more like a fluid. Buildings and infrastructure may tilt, sink, or collapse as a result. These effects are not caused directly by the fault movement itself, but by the way seismic waves interact with the local environment. Duration is another key aspect. Large earthquakes can produce shaking that lasts for a long time, especially in regions where waves are trapped or reflected. Extended shaking increases stress on structures and can lead to cumulative damage. It also affects human response, making it more difficult to maintain balance, evacuate, or carry out immediate protective actions. The experience of prolonged motion is one of the defining features of major earthquakes in Japan's large basins. Experts consider all these factors when assessing earthquake risk. They do not look only at the magnitude of potential events, but also at how seismic waves will interact with the complex geology of the region. This is why hazard maps include not only expected ground acceleration, but also information about soil type, basin structure, and potential amplification zones. The goal is to understand not just where an earthquake might occur, but how its energy will be distributed across the land. In this region of the story, the earthquake becomes a moving field of energy passing through a layered and varied crust. The waves that begin deep below the sea floor are transformed as they travel, shaped by the materials they encounter and the structures they cross. By the time they reach the surface, they no longer reflect only the size of the original rupture. They reflect the entire path they have taken through the earth. This is why ground motion in Japan can vary so widely from place to place, and why understanding the behavior of seismic waves is essential to understanding the full impact of an earthquake. Above the moving ground and the shifting water, Japan's built system forms the next inner layer of the earthquake story. This system includes homes, schools, hospitals, roads, railways, bridges, ports, power networks, water lines, factories, warehouses, communication systems, and the many hidden links that allow ordinary life to function from hour to hour. None of these structures stands apart from geology. Each is placed on land with a certain soil type, near a certain coast, along a certain slope, or above a certain faulted crustal block. When experts assess earthquake danger, they do not consider only the shaking itself. They also examine how the built environment receives that shaking, how it is damaged by it, and how failure in one part of the system can spread difficulty through many others. Japan is often recognized for strong earthquake engineering, and with good reason. Building codes have improved over decades. Structures are designed with better understanding of lateral motion, ductility, and energy dissipation. Ductility means the ability of a material or structure to deform without sudden collapse. Engineers use this principle so that buildings can bend and absorb seismic force rather than break in a brittle way. Many newer structures in Japan perform better in earthquakes than older ones built to earlier standards. Yet engineering strength does not remove all fragility. It redistributes risk, reduces certain forms of failure, and saves many lives. But it does not make every building or network immune to severe shaking, tsunami, fire, ground failure, or prolonged disruption. The age of structures matters greatly. Buildings erected before major revisions to seismic codes may be more vulnerable than later ones, especially if they have not been retrofitted. Retrofitting means strengthening an existing structure to improve its performance during earthquakes. In older neighborhoods, wooden homes, unreinforced masonry, and aging utility systems can still pose serious risk. Even when a building does not collapse, damage to walls, foundations, joints, ceilings, water pipes, and electrical systems may render it unsafe or unusable. This means that earthquake impact must be measured not only in deaths or total collapse, but also in loss of function. A hospital that remains standing but loses water, power, or access roads is still deeply compromised. Transport systems form one of the most sensitive parts of the built environment. Roads and railways connect cities, ports, mountain valleys, and industrial zones across a terrain that is narrow, steep, and densely used. Strong shaking can crack road surfaces, deform bridge bearings, damage tunnels, and trigger slope failures that bury roots beneath rock and soil. On flat reclaimed land or soft sediment, liquefaction can tilt embankments, distort foundations, and interrupt rail service. In coastal areas, tsunami may sweep debris across roads, flood tunnels, and isolate entire districts. Because Japan depends heavily on the rapid movement of people, supplies, and emergency teams, even partial transport failure can magnify the consequences of the original earthquake. Ports occupy a particularly exposed position within this system. They are essential for trade, fuel, food, and industrial activity, yet they often stand on low ground close to the water, much of it reclaimed. Reclaimed land is ground created by filling shallow coastal areas to produce usable space. Such land is practical and economically valuable, but it can be vulnerable to strong shaking and liquefaction. Quay walls may shift, cranes may be damaged, storage tanks may tilt, and access roads may be cut. If tsunami enters the harbour, moored vessels can break loose, and currents can continue to disturb the basin long after the first wave. Thus a port may suffer not from one mechanism alone, but from the combined effects of shaking, ground failure, inundation, and loss of supporting infrastructure. Power systems and communication networks add another layer of exposure. Electricity depends on generation plants, substations, transmission lines, transformers, control centers, and fuel supply chains. Communication depends on towers, cables, switching facilities, satellite links, and backup power. A major earthquake can damage these components directly or indirectly. Towers may remain standing while power is lost. Fuel may exist in storage but remain inaccessible because roads are blocked. Control systems may be intact but disconnected from the field equipment they govern. Modern societies are highly interdependent, which means that the failure of one network often weakens many others. Water pumping depends on electricity. Hospitals depend on both power and communications. Traffic control, emergency broadcasting, refrigeration, and financial systems all depend on stable energy and signal flow. Water and sanitation systems are equally important, though often less visible. Pipelines buried beneath streets can crack when the ground shifts. Treatment plants may lose power. Reservoirs and pumps may remain intact while distribution networks fail. In dense cities, loss of water affects not only drinking and hygiene, but also firefighting capacity. After strong earthquakes, fires can become a major secondary hazard, especially where gas lines are damaged and access for emergency vehicles is reduced. The built system is therefore vulnerable not only to direct mechanical damage, but also to the cascading effects of interrupted service. A city can remain partly upright in structural terms while becoming difficult to inhabit because essential systems no longer function. Industrial facilities present their own concerns. Refineries, chemical plants, heavy manufacturing zones, warehouses, and fuel depots are often concentrated along coasts and bays. This location provides efficient transport access, but increases exposure to both shaking and tsunami. Storage tanks may rupture. Hazardous materials may leak. Fire can spread through closely linked industrial complexes. The problem is not simply that such facilities are fragile in themselves. It is that they are embedded within larger urban and regional networks. Damage in one industrial district can affect energy supply, manufacturing output, employment, transport, and environmental safety across a wide area. Nuclear facilities receive especially close attention because the consequence of failure can extend beyond ordinary structural damage. Japan's history has shown that severe earthquake and tsunami events can challenge multiple safety systems at once, including off-site power, backup power, cooling systems, access routes, and emergency coordination. Nuclear plants are engineered with substantial safety measures, but experts remain careful because the required reliability is extremely high and because combined hazards can create conditions outside ordinary operating assumptions. The concern here is not based on ordinary building fragility alone. It arises from the need for uninterrupted control under extreme conditions and from the long reach of any serious loss of containment or cooling. The built environment also reflects social inequality and local variation. Some communities have stronger buildings, wider roads, higher ground, and better access to services. Others consist of older housing stock, narrower streets, steeper terrain, or more isolated coastal settlements. This means that vulnerability is not evenly distributed. The same earthquake can meet one district through well-retrofitted structures and multiple escape routes, while another faces it through aging homes and constrained evacuation paths. Experts therefore study fragility not only as a property of materials and design, but as a pattern shaped by geography, age, maintenance, and social organization. What makes the built system especially important is that it is where hazard becomes lived disruption. Plate boundaries, trenches, and seismic waves belong to the physical earth. Buildings and infrastructure translate those forces into loss or resilience. If structures remain usable, if roads stay open, if hospitals function, if ports and power systems recover quickly, then the deeper geological event is partly contained in human terms. If those systems fail together, the disaster grows far beyond the initial rupture. This is why experts do not assess earthquake risk by magnitude alone. They assess the condition of the built system that must endure the motion. In this inner region, the concern about earthquakes becomes practical and immediate. The built environment of Japan is advanced, disciplined, and shaped by long experience, yet it remains exposed because it is dense, interconnected, and partly coastal. Strength reduces risk, but dependence creates fragility. Every bridge, tunnel, pipe, quay, hospital, and control room forms part of a larger system that must continue to function under stress. Here the earthquake story reaches the structures of daily life, where the hidden forces of the plate boundary meet concrete, steel, timber, water lines, wires, fuel, and the routines of millions of people. At the innermost level of this subject lies the meaning of expert concern itself. By the time the story reaches this point, the outer setting has narrowed from the Pacific Basin to the plate margin, from the plate margin to locked sections, from locked sections to strain in the crust, from strain to past ruptures, signals, tsunami, shaking, and the built system that receives the impact. What remains is not another physical layer of earth, but the layer of scientific judgment that gathers all the others into a measured warning. When experts say that Japan's earthquake situation is worrying, they're not usually describing a single mysterious sign or a sudden break from normal conditions. They are describing a convergence of known factors whose combined weight is serious, even when the exact timing of the next major event remains uncertain. This distinction matters because public language often compresses risk into a simple image of coming disaster. Science does not work that way. A seismologist, geodesist, geologist, or disaster planner does not need certainty about the next date to recognize danger. Concern grows from the long record of large earthquakes, from measurements of strain accumulation, from the known geometry of major subduction zones, from the exposure of densely populated coasts, and from the history of severe tsunami and infrastructure disruption. None of these elements alone is the whole case. Together they form a pattern strong enough to justify steady attention. Expert worry is therefore not panic. It is disciplined recognition of a high-consequence setting that is continuously active whether or not a major event happens this year. The most important scientific limit remains the same throughout. No one can specify the exact day, place, and size of a future great earthquake with reliable precision. This limit is not a weakness unique to Japanese science. It reflects the nature of earthquake processes themselves. The plate boundary is buried, mechanically varied, and influenced by stress, fluids, temperature, rock type, and rupture history in ways that cannot be monitored perfectly. Instruments can measure crustal movement with extraordinary precision, but they do not read the fault as a clock. Historical patterns reveal recurrence, but not exact repetition. Slow slip, foreshocks, and unusual seismic sequences can raise concern, but they do not become a dependable schedule. This is why experts speak in terms of probabilities, scenarios, and preparedness rather than fixed prediction. Long-term probability is often misunderstood for this reason. A statement that a certain region has a high probability of a major earthquake over the coming decades does not mean that the event is certain tomorrow. It also does not mean that the danger is remote simply because it may not happen tomorrow. It means that, over the span of years relevant to planning, the accumulated evidence indicates a substantial chance of severe rupture. In the case of regions such as the Nankai Trough, this type of long-term assessment carries great weight because the historical record, tectonic setting, and modern geodetic measurements all point toward continuing strain accumulation in a margin capable of producing very large earthquakes. Concern is serious not because the exact moment is known, but because the underlying system has already shown what it can do. Consequences matter as much as likelihood. Experts judge danger partly by the expected scale of human and material disruption if a major earthquake occurs. Japan contains vast coastal cities, critical ports, industrial corridors, transport networks, and energy systems concentrated near active margins. This means that even when probabilities are spread over years, the possible impact of a single large event remains immense. A sober expert assessment therefore combines two questions. How likely is significant rupture over the planning horizon, and how severe would the consequences be if it occurred? Where both answers are large, concern becomes not dramatic but persistent. This persistence can seem paradoxical to the public. Years may pass without a catastrophic event, yet official concern remains. Then a moderate or large earthquake occurs, warnings briefly intensify, and later, the news cycle moves on while the scientific concern continues. The reason is that tectonic risk does not vanish with attention. It rises and falls only in limited ways after each release of strain. In some areas, a major rupture may reduce immediate stress on the section that slipped while increasing concern for neighboring sections. In other areas, long intervals of quiet may mean only that strain is continuing to build unseen. Experts, therefore, do not equate silence with safety. They examine whether the underlying drivers have changed. Often, they have not changed enough to reduce long-term risk in a meaningful way. Another part of expert concern involves communication itself. Scientists and public agencies must convey seriousness without overstating certainty. If they speak too vaguely, the public may not act. If they speak too absolutely, they may imply a precision that does not exist. This balance is especially difficult in Japan because the country is both highly prepared and highly exposed. Preparedness can create resilience, but it can also create the false impression that the problem is fully controlled. Repeated drills, strong building codes, and advanced warning systems are real strengths. At the same time, no level of readiness removes the underlying tectonic hazard or guarantees equal protection across all communities. Experts must therefore speak in a way that honours both truths at once. Their worry is also shaped by memory. The record of destruction from past earthquakes and tsunami is not abstract. It includes drowned coastal plains, broken ports, fires in cities, landslides in mountain districts, prolonged power loss, and long recovery from damage to homes, schools, and workplaces. These memories are not treated as emotional excess within scientific judgment. They are data carried through human experience. A nation that has repeatedly endured severe events does not need imagination to understand what a future rupture could mean. Expert concern grows sharper because the consequences are already known in broad outline, even if the next specific event is not. At this innermost level, the meaning of worry becomes clear. It is not a claim that catastrophe is inevitable at once. It is not a sign that science has found a secret signal pointing to one exact day. It is the recognition that Japan remains positioned above some of the most active and consequential plate boundaries on Earth, that parts of those boundaries continue to store strain, that the historical record includes repeated great earthquakes and tsunami, and that the built system above them remains exposed despite strong preparation. Concern is the correct response to such a setting. It is measured because the uncertainties are real. It is serious because the evidence is strong. So the expert voice, when heard clearly, says something quieter than alarm and stronger than reassurance. It says that the earth beneath and offshore of Japan continues its slow descent and resistance. It says that the known patterns of the past have not been erased. It says that the sea, the ground, and the structures of daily life remain linked to a plate boundary capable of sudden change. It says that prediction has limits, but responsibility does not, in that calm and demanding sense. Expert worry is not a mood. It is the final expression of all the physical layers beneath it, gathered into a single human conclusion that remains as steady as the tectonic motion itself. Night settles over the islands and the surrounding sea, and the long structure of the earth continues its motion below without hurry and without pause. Far out in the Pacific, plates still move through the darkness beneath the water, along the trenches and troughs. The ocean floor still bends downward. Within the buried boundary, some places remain locked while others move in slower ways. Above them, the crust continues its small changes of shape, too slight for ordinary senses, yet real enough to be measured. Along the coast, sea walls, roads, harbours, towns, and quiet homes wait within the same geography that has shaped them for generations. In this calm view, the subject becomes less dramatic and more enduring. Earthquake danger in Japan does not come from a single strange moment. It belongs to a deep arrangement of ocean, rock, stress, memory, and preparation. The past remains present in raised shorelines, buried sands, rebuilt districts, and the habits of evacuation and design. The future remains uncertain in its details, yet not empty of meaning. The great forces beneath the country are known. Their timing is not. So the final image is one of patience, The sea breathes at the edge of the land. The ground rests for now, though not in stillness. Instruments continue their silent watching. Scientists continue their careful measuring. Communities continue their routines above a moving world. Nothing in this scene promises safety without effort, and nothing in it justifies despair. It simply shows a country living within the terms set by its place on earth, where caution, memory, and knowledge remain the quiet companions of ordinary life,